So next we are going to do a very interesting experiment. What we are going to do is we are interested in looking at which are the most influential nodes in a network. And we have our answer also, right? So given a network over here, we saw that to find that, let's say in this network over here, this network over here, I want to see which nodes over here are the most influential. So what can I do is, we know that how do we define influence for a seed set. Given a seed, we'll start our independent cascade model from there, and we'll see that at the end how many nodes got infected. So to see that which nodes over here are most influential, what we can do is, first of all, we say that this is my seed. This is my seed, and then I perform the independent cascade model here, and I see that at the end how many people got infected, and let's say I found a value x1. Then I want to see the influential power of this node, so I'll set the seed to be this. Now this is no longer the seed. So this over here is the seed, only one node, and then I'll repeat the independent cascade model, and I'll see towards the end how many people got infected. I'll do for this, I'll do for this, do for this, do for this, do for this, and do for this. And at the end, we'll see that which of the x is maximum, and whichever x is maximum, that particular node is the node which is the most influential in this network. But doing this kind of an experiment, it's a very time consuming process, right? So taking every node to be seed node and again repeating the independent cascade model and then finding out influential node is a time consuming process. Here we have another very interesting question. Can you look at this network and then guess which is the node most influential over here? I have a feeling, for example, this node over here, it has 1, 2, 3, 4 neighbors and no other node, or maybe this node over here. So they have 4 neighbors. So probably might be they are most influential. Since they have more number of neighbors, they can infect more people, right? So it might be the case that these nodes are most influential. So that is an easy way of doing this same process, right? So taking every node over here and then running independent cascade model, as opposed to just looking at this network and looking at its structure, looking at the properties of certain nodes, and then saying that yes, this node is influential is quite easy. So now the question is, which nodes are the most influential over here? So we have various centrality measures. Okay, what is centrality measure? It's just a complicated term. So centrality measure is, we can measure the values of nodes over here based on certain things. For example, we can look at the degree of each node, right? So is it the degree? Can I say that the nodes which are having the maximum degree, they are the most influential nodes? Or we have another measure, let's say betweenness. I hope you remember what was betweenness. So betweenness tells me, if I look at a node, how important is it in connecting two different parts of the network? So let me use another example. Let's say there is a community structure. This is one community and this is one community, right? And there is a node over here. So this node over here is very instrumental in connecting these two portions of the graph. So this node has a very high betweenness over here, right? So are these the nodes which are having a very high betweenness, which are the most influential and will create the biggest cascade? Or are these the nodes having high closeness? So closeness is something like I take this node and I see that how close is it to other nodes in the network. For example, this node is very close to these 5 nodes, and then still closer to this node, and then far away from these nodes. So you can look it up. There is a very nice way of calculating this closeness centrality. But the intuition is simple. We see that how closer I am to the entire network, that is closeness. So are these the nodes which are having a high value of closeness, which are the most influential? Or we have a last measure which we discussed, coreness. So are these the nodes which are having maximum coreness, which are most influential? What do I mean by maximum coreness? Maximum coreness is, we know that all the nodes in this network are in one core, right? We define a value which is called core number. What is core number? It is nothing but the So see, a node can be part of one core, a node can be a part of two core, three core, right? Whatever is in three core, whatever node is in three core, that is automatically in one core. So let's say there is a node which belong to three core. I'll say that its core number is 3, right? Core number is 3. So the inner you are in the network, the innermost core you are towards let's say, let me put it like this. Okay, let me say that this is the network, and then in this network, this is the, so this is one core, right? So whatever is inside this particular circle is in one core, whatever is inside this particular circle is in two cores, so on and so forth. So we have 4 cores in this network. Now we know that a node which is present over here, right? A node which is present over here, it's a part of one core as well as two core as well as three core as well as 4 core, right? But it is the innermost. So I'll say that the core number of this node over here is 4. The core number of all the nodes which are present over here is 3. The core number of all the nodes which are present here is 2, and which are present here is 1. So are these the nodes which lie over here which are the most influential? Has the influential power something to do with the coreness of a node, which is the core number of a node? So this thing is what we want to look at. So how we are going to do it is, we are going to take a network. So I'll take a network over here. We will be doing it next in our next programming screencast. So I'll take a network over here. What we are going to do, we are going to take degree of the nodes, and we are going to arrange these nodes in descending order of their degree. So node which has the maximum degree comes over here, and the node which has the minimum degree comes over here. Let's say something like this. And similarly, we are going to look at betweenness, and we are going to arrange these nodes having the highest betweenness over here, least betweenness over here. Similarly, we are going to do for closeness, and we are going to do for coreness. And our aim is to see which out of these 4 measures is most related to the influential power of a node. So we'll take a new list corresponding to the influential power. In influential power, we'll actually take nodes and determine their influential power. So I'll take this node over here and run independent cascade model from it, and then see what is its influential power. Say I1. Going to do this for this same node I2, and then here I'll arrange the nodes in the descending order of their influential power. So let's say BCZA. Right, so I've arranged the node here according to their influential power, and then we'll compare these lists. So we'll see at whether these are the nodes having highest degree, which have the highest influential power, or these are the nodes having highest betweenness, which have highest influential power. And to our surprise, not surprise, can't call it surprise, but we'll see that actually these are the nodes having the highest value of coreness, which best defines which are the most influential nodes in a network. So what we are going to do now is, we are going to look at different nodes, arrange them according to sorted degree, closeness, betweenness, coreness, and their cascading power, and then see which of the centralities match the most with the influential power of a node. Where influential power is of a node is, if you select that particular node as seed for your infection, how many nodes are infected by the end of your process. So what we are going to do here now is, we are going to use the same code which we have written previously for the independent cascade model. Okay, so we are going to make 4 dictionaries now for holding different values. A dictionary for holding the degrees of nodes, a dictionary for holding the closeness of nodes, let's call it CL for simplicity, and then a dictionary for holding the betweenness of nodes, let's call it BW, and then a dictionary for holding the core numbers of nodes, which are found by Casial decomposition, and let's call that coreness, denoted by CR. Okay, so we have these 4 dictionaries, and now we are going to flood these dictionaries. How do we put in the values for these dictionaries? For each in g.nodes, what we are going to do is, dictionary for degree, the value corresponding to the key each, which is the node E, is the degree of that node, G dot degree each, right? And then dictionary corresponding to the closeness each. So there is a function in network X, you can directly calculate the closeness of a node, and it is called nx dot closeness centrality. You can look it up, nx dot closeness centrality, and then we are going to put G comma each here. And there is a similar function for betweenness. BW is nx dot, and this is simply called betweenness centrality. So betweenness. And a surprise for you, I hope you didn't know it earlier, otherwise you wouldn't have watched the previous programming screencast. You can actually get the core number of a node directly with the help of network X, with the help of the function known as core number, which performs K-shell decomposition on a network and gives you the core number for a given node. Right? Okay, and here you see that the notation is a little bit different. Why? So when you use nx dot core number G, nx dot core number G is nothing but a dictionary. In that dictionary, we want, so these are the values. So these are the functions which returns you the values. Nx dot core number is a function. So this is a function which returns you a dictionary, and from that dictionary you want the value corresponding to the node each. So that's why we have wrote it in this manner. So we got the dictionaries corresponding to all these four centralities, and at the end what we need, we are creating our own dictionary which holds the cascading power of nodes. So we have a dictionary for that. And how do we flood this dictionary? We have to flood this dictionary using our independent cascade model. So how do we do that? So in this, one by one we will select every node in this network as seed. So we'll take 1 as seed, 2 as seed, and what we will do to as we know, when we run this independent cascade model, it's quite a random process, right? So we'll run it some 1000 times. So we'll take 1 as seed, run independent cascade model from this 1000 times, and take the average number of nodes which are getting infected. So what do we do? For each in G dot nodes, what we are going to do is, C is currently empty, and then we take a loop which runs 1000 times for num in range 0 to 1000, and what we are going to do, we set the seed of the process to be equal to each, and then we call our independent cascade model with graph G and seeds. So now this value I over here is nothing but a list which holds the final people infected when the seed was the one node each here. So what do? We append this length of I in our array C, right? So some 1000 times we get different people who are infected for different processes, and for all these 1000 times we append the number of people who were infected in this array C. So this array C will be consisting of 1000 entries, and each entry will correspond to one process where this node each was infected, and some people were infected by the end of the process. And now what I am going to append in my dictionary cascade, dict cascade each, is the average from C. That is, on an average, how many people got infected if I started my infection from this node each, right? And then what I am going to do now is, I have found out 5 dictionaries, one for degree, closeness, betweenness, coreness, and one for cascading. And now I want to see which out of these 4 correlates the most with this one, which is our degree for cascade. So what I am going to do is, I am going to sort all of these dictionaries. So sorting is easy with one command. So let's first sort this dictionary corresponding to cascade. So there is a function sorted which you can call on a dictionary. So you pass your dictionary cascade here, right? And we want to sort according to the keys are going to be nothing but dictionary cascade dot get, and we want to sort them in a reverse order. So we set reverse equals to true, and we do this with all our dictionaries, with all the remaining 4 dictionaries. So this cascade thing we can, for degree we replace it with degree, and for closeness we replace it with CL, and for betweenness we replace it with BW, and here also BW, right? And for coreness we replace it with CR, okay, CR. And we can actually print all of these and see what is happening. Print, let's print degree first, and then let's print degree, and then let's print closeness, and then let's print betweenness, and then coreness, and then cascade, right? Let's implement it and see. Okay, so we have used this numpy module for finding the average. We need to import it. So import numpy as NP, and actually we were printing some extra values. Were we printing some extra values? Okay, not sure. We are actually printing. Okay, so we don't want to see all these values because so many times our process have run. Okay, so we can actually, we don't need this portion of the code, and let's now run it and see. And okay, we don't know where one particular list is ending. So let's say here print sorted degrees. So these are your nodes sorted according to degree, according to closeness, according to betweenness, according to coreness, and according to, we can call it nothing but the influence. Okay. Okay, fine. So we have many extra things printed here which we actually don't want. From where this print statement is coming. Okay, so it's coming from here. We can actually comment it and run it again. Still something is printing. S is printing here. We'll comment it also. Okay, see here. So these are your nodes sorted according to your degrees, nodes sorted according to closeness, betweenness, coreness, and influence. So what I have done, I have actually run this process and I have kept these values here. So these values might not be exactly the same. So for degree and closeness, these are going to be exactly the same. So if you see here 5, 13, 14, 15, it's going to be the same 5, 13, 14, 15. For finding out the betweenness, we use a random process. The algorithm uses a random process. So the value here might not be very same as what is here. And for coreness, it's going to be the same. And for influence, it's mostly going to be the same because we have run this process 1,000 times. So the results which we are going to get will be the same, 13, 15, 14, 10, and you can see 13, 15, 14, 10 and so on. Okay, let's analyze what's happening. So here I have taken a spreadsheet. Here I have put nodes according to descending order of degree, descending order of closeness and so on. Now I want to show you here something. Do you see here this cascadeness? It's actually nothing but the influence. So it is the influence here. Okay. So if you see here, you see the node which is having the highest influence is the one having the highest coreness and actually the highest closeness. Okay. It means that maybe closeness and coreness relates to influence. But if you look at the second highest node here, which created the second highest cascade, it has a high coreness, but it doesn't have a high closeness. So overall, you can see that this influence over here is mostly related to the coreness and degree. So closeness, if you see nodes 10, 5 and 11 here, this goes quite down here, and then this node 8 here comes over here. So the influence is maximally correlated with the coreness and degree here, and out of coreness and degree also you can see that it's mostly related to coreness. This node 5 over here has a very high degree, but it has a very less influential power. So this result, it validates that if you want to look at the maximum influential power of a node, you should look at the nodes which are having the maximum coreness. So I have done this experiment over here for one network. You can actually replicate this experiment for various different networks. Rather, you can use some real world data sets also and verify this.